A black hole is a place where the laws of physics break down. This single point in space, with gravity so powerful it traps light itself, is one of the universe's ultimate mysteries. By the end of this exploration, you will possess a completely new understanding of reality itself. We are going to uncover 25 astonishing facts about these cosmic enigmas, facts that reveal how they can warp time, tear stars apart, and might even whisper the secrets of creation. What do you believe lies at the heart of such absolute darkness? That absolute darkness is defined by a boundary more final than any wall. This is the event horizon, the point of no return. Think of it not as a physical surface, but as the ultimate one-way door in the cosmos. Once you cross this invisible threshold, the gravitational pull becomes so intense that the speed required to escape exceeds the speed of light itself. Since nothing in our universe can travel faster than light, the conclusion is stark and absolute. There is no return, not for you, not for your spacecraft, and not even for the light reflecting off your helmet. It is the moment you cease to be part of our observable reality. Physicist David Finkelstein first formally described this concept in 1958, revealing a profound implication of Einstein's equations of gravity. The event horizon is not a place of dramatic turbulence or visible fire. If you were to approach it, you might not even realize the exact moment you crossed over. But the view would be utterly surreal. Looking back outward, you would witness the entire history of the universe behind you playing out in a frantic, blue-shifted blur, as time itself stretches and warps under the black hole's immense gravity. It would be your last distorted glimpse of everything you once knew, a farewell stretched across eons from your perspective. This boundary creates one of physics' greatest puzzles, known as the information paradox. If matter and energy that fall in are lost forever, what happens to the information they carried? Does the universe simply forget? This question consumed minds like Stephen Hawking's, challenging our very understanding of reality. The event horizon is more than a line in space. It is the ultimate cosmic secret keeper, guarding the mysteries within. And the force that creates this impenetrable boundary, the sheer weight that warps the fabric of space itself, is born from a collapse of almost unimaginable scale. The sheer power that creates the event horizon has a bizarre and deeply personal consequence for anything that ventures too close. This is the second astonishing fact, a process with a name that sounds almost playful, spaghettification, but describes a reality of absolute cosmic violence. It reveals that falling into a black hole is not a simple plunge into darkness. If you were to approach a typical stellar mass black hole feet first, the gravitational pull on your feet would be catastrophically stronger than the pull on your head. This difference in force, known as a tidal force, would stretch you lengthwise. Simultaneously, the sides of your body would be compressed inward by the same intense gravity. The result is not a quick end, but a grotesque transformation. You will be pulled into a long, thin strand of atoms, a single thread of what was once a human form, resembling a piece of cosmic spaghetti. This vivid term was popularized by Stephen Hawking to make an unimaginable concept graspable. For a black hole with the mass of a few suns, this stretching and tearing would occur far outside the event horizon. You would be completely dismantled, the very structure of your matter taken apart, before you ever crossed that final boundary of no return. This is not a quiet swallowing, it is a loud and violent unraveling of reality itself. As matter is torn apart in this way, it doesn't just vanish silently. The atoms are heated to incredible temperatures through friction and collision, releasing powerful bursts of X-ray energy that astronomers can sometimes detect across the galaxy. So in a strange twist, the catastrophic end of an object becomes a fleeting signal, a data point of extreme physics. This process shows that black holes are not just passive holes, they are active shredders of the universe, transforming orderly structures into streams of fundamental particles. And this extreme distortion is merely a prelude, a hint of the far more profound and warped reality that governs the very center of the darkness, a place where the laws of physics as we know them cease to exist entirely. That terrifying process of spaghettification requires you to be exceptionally close, a reality that corrects one of the most persistent myths about these objects. Black holes are not cosmic vacuum cleaners. They do not roam the galaxy, voraciously sucking in everything in their path. In truth, their gravitational pull at a distance is no stronger than that of any other object with the same mass. Picture our own sun. Its gravity holds the planets in their steady orbits. If you could, in an instant, magically replace the sun with a black hole of exactly the same mass, nothing about Earth's orbit would change. Our planet would continue circling that point of absolute darkness, locked in the same gravitational embrace, just plunged into permanent night. The danger exists only in an extremely close and specific zone, right near the event horizon. This distinction is crucial. It transforms our understanding from seeing black holes as omnipotent, all-consuming monsters to recognizing them as powerful but localized phenomena, governed by the same universal rules of gravity as everything else. Astronomer Andrea Ghez, who shared the Nobel Prize for her pioneering work, provided stunning proof of this. For decades, she and her team tracked stars whipping around the supermassive black hole at the heart of our Milky Way. These stars, with orbits lasting years or decades, have danced this perilous cosmic ballet for millions of years without being consumed. They are like satellites in a stable, if extreme, gravitational field. A black hole's diet is not a matter of active hunting, but of circumstance. It primarily feeds on matter that strays too close on its own, or from material that is funneled toward it from a companion star in a binary system. This corrects the dramatic Hollywood image of a black hole as a relentless predator moving through space. In reality, they are more like powerful, passive anchors in the fabric of spacetime. Their terrifying reputation is earned entirely by what happens at their boundary, not by their long-range reach. Understanding this allows us to see them as natural, albeit extreme, parts of the galactic ecosystem. Their generally quiet nature makes their rare moments of activity, when a large cloud of gas or a star does wander too close, all the more spectacular and informative for astronomers. And when such a feast begins, the black hole does not eat neatly. The process creates a chaotic, swirling disk of doomed material that glows with the heat of a billion stars, revealing another astonishing layer of their behavior. While a typical black hole is born from a single star's death, the universe holds a far more dominant and mysterious kind. At the very heart of nearly every large galaxy, including our own Milky Way, rests a cosmic monarch, a supermassive black hole. These are not stellar corpses but incomprehensible giants, containing the mass of millions or even billions of suns all crushed into a single point. Their origin story is one of astronomy's great open questions. Did they form directly from the collapse of immense primordial gas clouds in the chaotic infancy of the cosmos? Or did they start as smaller seed black holes that grew insatiably over billions of years by consuming stars and gas? We simply do not know yet. Our own galactic center is home to one such behemoth named Sagittarius, a star. It is 4 million times the mass of our Sun, yet it is currently quiet, a slumbering giant. But its presence is felt. Stars whip around it at breathtaking speeds, tracing orbits that reveal the immense, hidden weight they are bound to. In other galaxies, these monsters are awake and feeding. When vast amounts of matter spiral into their gravitational grip, the infalling material heats up to millions of degrees, unleashing a torrent of radiation so brilliant it can outshine the entire galaxy that hosts it. We see these phenomena as quasars, the most luminous beacons in the universe, all powered by a supermassive black hole's feast. In April 2019, the Event Horizon Telescope collaboration achieved the impossible, presenting humanity with the first ever direct image of a black hole's shadow, specifically the supermassive one at the core of the galaxy Messier 87. That now iconic orange ring of light surrounding a dark central void was not just a scientific triumph, it was a visceral confirmation of these titans' reality. Their role extends far beyond being passive occupants. Astronomers now believe these supermassive black holes are fundamental architects. Their gravity likely acts as a cosmic anchor during a galaxy's formation, and their intense energy output during active phases can regulate star birth across vast regions, heating or expelling the gas needed to form new suns. This suggests a profound and elegant connection, a hidden dialogue between the largest structures we see, the majestic swirls of galaxies, and the most extreme objects we can conceive, points of infinite density. Their silent, dominant presence in every galactic core forces us to reimagine the cosmos not as a collection of isolated stars, but as a tapestry woven around these profound gravitational knots. And just as these giants shape galaxies, their smaller stellar cousins engage in a far more intimate and destructive dance, one that can tear a star apart in a cataclysmic display. The ultimate fate of that star being torn apart is governed by a force that warps the very fabric of existence itself. Gravity around a black hole does not just bend the paths of objects, it twists the dimension of time. Einstein's theory of general relativity revealed that gravity is the curvature of spacetime, and a black hole is the most severe warp possible. This leads to a mind-bending fact. Time itself slows to a crawl near the event horizon. Imagine two identical clocks, one placed on a spaceship in a safe orbit, and another sent on a doomed mission toward the black hole. From the perspective of the orbiting astronaut, a bizarre and haunting scene unfolds. As the descending clock approaches the event horizon, its ticking would appear to stretch out, becoming slower and slower. Its light would shift to longer, redder wavelengths, dimming as it struggles to climb out of the gravitational well. At the precise boundary of the event horizon, from the outside observer's view, time for that falling clock would appear to stop completely. The clock would seem to freeze, its last photon of light stretched into infinity, fading from view not with a flash, but with an eternal, redshifted whisper. It becomes a ghost image permanently etched onto the boundary from our perspective. Yet here is the profound paradox. For the astronaut riding with that clock, none of this dramatic slowdown is felt. Their own heartbeat, their watch, their thoughts all proceed at a normal rate. They would cross the event horizon in a finite amount of time, completely unaware of the eternal tableau they have left behind for the universe to see. This creates two equally valid yet utterly incompatible realities. For the outside cosmos, the falling object never quite finishes its fall. For the object itself, the fall concludes. There is no single universal now, a concept that shatters our everyday intuition. Physicist Kip Thorne has extensively explored these dizzying implications, showing how black holes force us to abandon a common-sense view of time. This is not merely theoretical. We confirm this time-warping effect every day with the Global Positioning System. The atomic clocks on GPS satellites, experiencing slightly weaker gravity in orbit, run faster by a tiny fraction of a second compared to clocks on Earth. Engineers must correct for this or the system would fail within minutes. At a black hole, this subtle effect is amplified to its absolute, logical extreme. Time dilation is the ultimate expression of gravity's power, proving that time is not a rigid backdrop for the universe, but a malleable, dynamic player in the cosmic drama. And if time can be stretched to a standstill, then the very information carried by light and matter faces a bizarre and controversial fate, leading to one of the greatest debates in modern physics. The frozen clock at the event horizon presents a profound problem for physics because it suggests information is lost forever. But what if nothing, not even a black hole, is truly eternal? Stephen Hawking delivered a shocking answer that redefined our understanding. He proposed that black holes are not perfectly black and they are not permanent. They can, over timescales so vast they dwarf the current age of the universe, slowly evaporate and vanish. This glow of particles escaping a black hole's grip is known as Hawking radiation. The mechanism is a strange and beautiful dance between the large-scale warping of space and the tiny, probabilistic world of quantum physics. According to quantum theory, empty space is not truly empty. It is a seething sea of virtual particles, pairs of matter and antimatter that spontaneously pop into existence, borrow energy from the vacuum, and then almost instantly collide and annihilate each other, returning the energy. This happens everywhere all the time, but at the very edge of a black hole's event horizon, this quantum fluctuation meets the ultimate gravitational cliff. Imagine one of these particle pairs appearing right at that precipice. In a rare and fleeting moment, one particle might fall across the boundary into the black hole, while its partner escapes outward into the universe. The escaped particle becomes real, carrying away a tiny amount of energy. To conserve energy, that energy must come from somewhere. Hawking realized it comes from the black hole itself. The black hole loses an infinitesimal amount of mass. For a black hole with the mass of a star, this process is so incredibly slow it is utterly negligible. The faint trickle of Hawking radiation is drowned out by the cosmic microwave background, the afterglow of the Big Bang. The black hole would take many, many times the current age of the universe to evaporate in this way. But the implication is staggering. It means black holes have a temperature, a concept that links them to the laws of thermodynamics. It also gives them a potential end. For a hypothetical tiny black hole, one that might have formed in the extreme conditions of the early universe, the story is different. A primordial black hole with the mass of a small mountain would be radiating away energy furiously by these cosmic standards. Its final moments would not be a quiet fading, but a sudden, violent release of energy, a flash of radiation marking its departure from reality. Hawking's brilliant insight did more than predict a faint glow. It wove together the two great but conflicting theories of modern physics, Einstein's general relativity and quantum mechanics. It suggested that even the darkest, most absolute objects in the cosmos are subject to the subtle, probabilistic rules of the quantum world. This revelation transforms the black hole from a permanent cosmic tomb into a temporary, if immensely long-lived, phenomenon with its own slow, quiet heartbeat of quantum evaporation. And if a black hole can fade away, what becomes of everything it ever swallowed? This question leads to a paradox that has divided physicists for decades, a battle over the fundamental nature of information in our universe. Hawking's paradox of evaporating black holes forces us to confront the ultimate mystery, the final destination of all that swallowed matter. According to Einstein's equations, it is crushed into a point of infinite density, the singularity. This is not a solid object you could touch, but a mathematical boundary where the fabric of spacetime itself becomes infinitely curved and simply ceases to exist as we understand it. It is the place where the roadmap of general relativity, our best description of gravity, dissolves into meaningless scribbles. The equations produce infinities, a clear signal that our physics has reached its limit. The singularity is the ultimate cosmic dead end, a one-way street to a realm with no known rules. For decades, this was the accepted, if unsettling, picture. Yet the quest to understand what truly lies at the center has become the most thrilling frontier in theoretical physics. The infinities are seen not as an answer, but as a challenge, a sign that we need a deeper theory that unifies the vast scale of gravity with the tiny, probabilistic world of quantum mechanics. In this search, the singularity might not be a point at all. Some proposals within string theory suggest the heart of a black hole could be a tangled, vibrating ball of fundamental strings, a fuzzball with a defined, though incredibly dense, structure. Another idea from loop quantum gravity imagines a rebound where matter is compressed to the smallest possible scale, the Planck length, and then bounces back, potentially as the seed for a new universe. These are not wild guesses, but rigorous mathematical attempts to avoid the paradox of infinity and describe a reality where physics does not break down. The most tantalizing possibility is that the singularity could be a tunnel, a wormhole bridge connecting our region of spacetime to another, or to a distant part of our own universe. While this remains speculative, it transforms the black hole from a mere destroyer into a potential cosmic connector, a hidden doorway in the architecture of reality. The singularity, therefore, is more than a scientific puzzle. It is a profound philosophical mirror reflecting the limits of human knowledge. Staring into that darkness, we are not just looking at a collapsed star, we are confronting the boundaries of our own understanding and glimpsing the shape of a future physics that lies just beyond our current reach. This relentless compression of matter hints at another bizarre possibility, that black holes might not be unique, but could come in forms even stranger than we have yet imagined. That crushing gravitational grip at the singularity is not the end of a black hole's story, because many of these cosmic objects are in constant, dizzying motion. They can spin at speeds approaching the very limit set by the universe itself. This rotation is a direct inheritance from the stars that gave them birth. Just as a figure skater pulls in their arms to spin faster, a massive star's core collapses inward at the end of its life, dramatically increasing its rate of spin. The result is not a static pit, but a whirlpool in the fabric of spacetime. This type of black hole is described by a solution to Einstein's equations found by physicist Roy Kerr, and it reveals a far more complex and active beast than a simple, non-spinning one. The key difference is an astonishing phenomenon called frame dragging. Imagine stirring a cup of honey with a spoon. The honey closest to the spoon is pulled along most strongly. In a similar but vastly more profound way, a spinning black hole does not just pull on matter, it drags the very fabric of space and time around with it as it rotates. This creates a warped region just outside the event horizon called the ergosphere, a name derived from the Greek word for work. Within this oblong shell, it becomes impossible to stand still. No matter how powerful your rockets, you cannot resist the current. Spacetime itself is flowing like a cosmic river, and you are caught in its relentless pull. This is not just a theoretical curiosity, it is a potential powerhouse. The incredible rotational energy stored in the ergosphere could, in principle, be extracted. Advanced civilizations, in theory, might one day harness this by dropping matter into the ergosphere and collecting the energized debris that gets flung out. It is a concept that transforms the black hole from a consumer into a potential battery of unimaginable scale. This ferocious spin has visible, spectacular consequences. As matter spirals in through the accretion disk, the black hole's rotation can funnel some of it into focused beams that erupt from its poles. These are relativistic jets, streams of charged particles accelerated to nearly the speed of light, shooting across thousands of light years. They are among the most energetic phenomena in the cosmos, and they are direct products of a black hole's spin. Measuring this spin is a major goal for astronomers as it tells a story. A very fast spin suggests the black hole grew steadily by feeding on a consistent flow of material from one direction, like a steady diet that kept it spinning. A slower spin might indicate a more chaotic history of mergers with other black holes, which can cancel out rotational momentum. So by observing the effects of frame dragging and the power of its jets, we can read the autobiography of the black hole written in its rotation. This dynamic property shatters the image of a black hole as a simple, dark pit. It is an active, energetic engine, a cosmic vortex whose spin imprints itself on everything nearby and reaches out to shape the galaxy around it. And if a black hole can spin, then two of them can also perform a gravitational dance of catastrophic proportions, leading to events that literally shake the universe. The incredible spin of a black hole channels its energy outward, but when that energy is fully unleashed, it creates a spectacle that defies all expectation. A supermassive black hole in its feeding phase becomes the engine for the most luminous objects in existence. We call them quasars, and their brilliance is almost beyond comprehension. Picture a single point of light, so fierce and concentrated that it can outshine the combined glow of every single star in an entire galaxy. Hundreds of billions of suns, all from a region not much larger than our solar system. This is not the light of nuclear fusion like in stars, but something far more potent. It is the light of gravity itself, converted into radiation with breathtaking efficiency. As vast rivers of gas, dust, and even whole stars spiral inward, they form a seething, flattened whirlpool called an accretion disk. The material in this disk does not fall in peacefully. It is a cosmic traffic jam of epic proportions, with particles rubbing against each other at tremendous speeds. This friction, along with powerful magnetic fields twisted by the black hole's spin, heats the gas to temperatures of millions of degrees. Matter this hot does not just glow, it screams across the entire electromagnetic spectrum, from radio waves to visible light to deadly X-rays. Some of the infalling material, instead of crossing the event horizon, gets caught in the black hole's magnetic grip and is rocketed away at nearly the speed of light in two narrow, opposing beams. These relativistic jets can stretch for hundreds of thousands of light years, punching through intergalactic space like celestial searchlights. For astronomers, these brilliant beacons are gifts. Quasars are so intensely bright they can be seen from the farthest reaches of the observable universe, acting as cosmic lighthouses that illuminate the ancient structure of space itself. By studying their light, we peer back to a time when the cosmos was young and chaotic. Yet this dazzling output has a profound and paradoxical effect on its home. The torrent of energy and particles from the quasar or its active galactic nucleus acts like a cosmic hurricane, blowing away the very gas clouds that would otherwise collapse to form new stars. In this way, the supermassive black hole becomes a galactic regulator, its feast ultimately putting a limit on the growth of its own host galaxy. It is a stunning cycle of creation and suppression, all governed by gravity's darkest pit. The black hole, a symbol of ultimate darkness and consumption, is also the catalyst for the universe's most brilliant light shows, a reminder that in the cosmos, destruction and creation are often two sides of the same coin. That brilliant light from a feeding black hole is only one side of the story, for these objects can also speak in a language far more subtle and profound. In September 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, heard the universe whisper for the first time. They detected not light, but the faint, trembling ripples in spacetime itself, gravitational waves, generated over 1 billion light-years away by the final, frantic dance of two black holes spiraling toward a cataclysmic merger. This was the chirp heard around the cosmos, a direct confirmation of a prediction Albert Einstein made a century prior. Imagine the fabric of spacetime as the surface of a still pond. The merger of two black holes is like dropping two immense weights into that pond. The impact sends waves racing outward in all directions, stretching and compressing space itself as they pass. LIGO's incredibly sensitive instruments, with arms 4 kilometers long, are designed to catch these infinitesimal stretches, smaller than the width of a single proton. The signal they captured, when sped up and converted into sound, was a brief, rising chirp that culminated in a final, defining thud. That sound tells a violent love story. For millions of years, these two black holes likely orbited each other in a slow, silent waltz, gradually losing energy by radiating gravitational waves. As they drew closer, their dance accelerated, the chirp rising in pitch and volume until, in a fraction of a second, they collided and became one. In that instant, the energy released in gravitational waves was greater than the combined light output of every single star in the observable universe. It was the most powerful event humans have ever measured, yet by the time those ripples reached Earth, they were an almost imperceptible tremor, a testament to both the violence of the event and the vast, quieting distance it crossed. This new sense, this ability to hear the cosmos, has revolutionized astronomy. From a single chirp, physicists can listen and discern the masses and spins of the black holes that created it, building a census of dark objects invisible to telescopes. They learn that the new black hole born from the collision is always slightly less massive than the sum of its parents. The missing mass is not lost, it is the precise price paid in pure energy, radiated away as the gravitational wave signal that tells us the tale. Each detection is a snapshot of a hidden, dynamic universe, one where black holes are not lonely monsters, but partners in a gravitational tango that occasionally ends in a universe-shaking embrace. And if we can hear the collisions of stellar mass black holes, what might we one day hear from the mergers of the supermassive giants that anchor entire galaxies? The violent mergers heard by LIGO create new black holes, but their masses tell a curious story. Most fall into two distinct categories: the stellar mass remnants of dead stars and the supermassive giants anchoring galaxies. For decades, a crucial middle ground seemed empty, a puzzling gap in the cosmic family tree. Where were the intermediate mass black holes, the missing link between the small and the impossibly large? These would be cosmic adolescents, weighing between 100 and 100,000 times the mass of our Sun. Their existence is more than a matter of cataloging. They are the hypothesized building blocks, the potential seeds from which the supermassive behemoths could have grown in the frantic early universe, yet spotting them proved incredibly difficult. They are not massive enough to power brilliant, galaxy-dominating quasars, and they are not commonly found in tight binary systems with a visible star, the way we detect many stellar mass black holes. They are the cosmic quiet ones lurking in the shadows. The hunt for them turned to dense stellar environments, like the hearts of ancient globular clusters. Here, theorists suggested, a runaway process could occur. Smaller black holes could sink to the cluster's center through gravitational interactions, meet, merge, and over eons, build up into a single intermediate mass object through repeated collisions. Then, in September 2020, a gravitational wave observatory heard a signal unlike any other. The event, named GW190521, was the collision of two immense objects. The resulting black hole weighed a staggering 142 solar masses, placing it firmly in that elusive intermediate range. This was not just a detection, it was a revelation. It proved that black holes in this mysterious mass class do form and merge in the darkness. Another compelling candidate was found in a bright burst of X-rays from the edge of a distant galaxy, evidence of a star being torn apart not by a supermassive giant, but by a mid-sized predator of about 50,000 solar masses. Each clue is a piece of a grander puzzle. If these intermediate black holes are common, they could solve a pressing mystery. How did the supermassive black holes at the cores of galaxies become so enormous so quickly after the Big Bang? Having these ready-made heavy seeds already in place would give them a colossal head start. Their confirmed existence would complete the evolutionary picture, showing a continuous path of growth from the death of a star to the monarch of a galaxy. The search for these cosmic middle children is one of astronomy's most active pursuits, a hunt for the missing chapters in the biography of darkness. And if black holes can grow through such violent mergers, what other bizarre objects might be formed from the wreckage of these cosmic collisions? The merger of two black holes creates a new object defined by just 3 numbers. This profound simplicity is captured by the famous No-Hair Theorem. In the equations of general relativity, a black hole is the ultimate cosmic minimalist. No matter how complex the star that birthed it, or what strange collection of planets, asteroids, or spaceships later fell in, all of that intricate information is seemingly erased. The resulting black hole can be completely described by only its mass, its electric charge, and its spin. Everything else, every detail about the atoms that built it, is lost forever. The metaphor is vivid. A black hole has no hair, no distinguishing features beyond those 3 bald facts. It is the universe's most efficient shredder of complexity. This theorem presents a beautiful, if unsettling, elegance. It suggests that black holes are the ultimate simplifiers, reducing the rich diversity of the cosmos down to a few simple parameters. Yet this very elegance clashes violently with a cornerstone of quantum mechanics, which states that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is the heart of the black hole information paradox, a conflict that has divided physicists for decades. If the No-Hair Theorem holds, then black holes are unique violators of a fundamental quantum law, creating true randomness and erasing the past. But what if the theorem is incomplete? Some modern theories, particularly those venturing into quantum gravity, propose a radical alternative. They suggest that information is not obliterated at the singularity. Instead, it might be preserved in some form on or near the event horizon itself. The infalling matter could leave a faint quantum imprint on this boundary, a subtle kind of cosmic braille. In this view, black holes might indeed have hair, but it is quantum hair, fantastically fine and complex, encoding the history of everything that ever crossed the threshold. Stephen Hawking himself eventually came to believe that information could escape, not by conventional means, but slowly and chaotically through the very Hawking radiation that causes a black hole to evaporate. The information would be there, but scrambled into what he called a form of cosmic static, a message encrypted with a key of unimaginable complexity. Decoding it would be a task of godlike proportions. This debate is not just academic hair splitting, it cuts to the core of how we understand reality. Are black holes the ultimate dead ends, the universe's trash compactors? Or are they the most secure and sophisticated libraries in existence, storing every bit of data that ever entered them in a quantum script on their surface? The search for an answer is pushing the boundaries of mathematics and imagination, forcing us to question whether the fabric of spacetime itself has a granular, holographic nature where a volume of space can be fully described by information painted on its bounding surface. The theoretical possibility of hair means that within the apparent void, a universe of hidden stories might be waiting, written in a language we are only beginning to decipher. The idea that a black hole could erase all information is a paradox born from its immense power, a power that can also be harnessed for a different kind of creation. The chaotic whirlpool of an accretion disk and the focused fury of its relativistic jets do more than just produce light. They act as nature's ultimate particle accelerators, achieving energies that make our most powerful machines on Earth seem like child's toys. At facilities like the Large Hadron Collider, we accelerate protons in a controlled ring to a fraction of the speed of light to smash them apart and reveal fundamental particles. Around a black hole, this process happens on a cosmic scale with almost unimaginable force. Charged particles, like electrons and protons, become trapped in the immensely powerful magnetic fields that are twisted and amplified by the black hole's spin. These fields act like a slingshot of cosmic proportions, whipping particles around in tighter and tighter spirals until they are hurled outward at velocities incredibly close to the absolute speed limit of the universe. When these ultra-fast particles inevitably collide with each other or with photons of light, they do not just bump gently. The impacts are so violent they can forge entirely new particles and release the most energetic form of light in existence, gamma rays. This is not a gentle glow, it is a scream of pure energy from the edge of spacetime. Some astrophysicists now look to these natural accelerators to solve a long-standing mystery. Occasionally, our planet's atmosphere is struck by cosmic rays with energies so stupendously high that a single subatomic particle can carry the kinetic energy of a professionally thrown baseball. For decades, the source of these ultra-high energy cosmic rays was unknown. The leading hypothesis points directly to the relativistic jets erupting from supermassive black holes in distant active galaxies. These jets, stretching across millions of light-years, are perfect candidates. They provide the sustained, powerful magnetic environment needed to accelerate a proton or atomic nucleus to such an insane degree. Telescopes like the Fermi Gamma Ray Space Telescope have mapped the sky in this high-energy light, and the bright, blazing sources they find are often the jets of these monstrous black holes. This transforms our understanding of their role once again. A black hole is not merely a consumer of matter or a source of light. It is a fundamental physics laboratory, operating under conditions we could never hope to recreate. By studying the gamma rays and particles they generate, we are not just learning about gravity and accretion. We are probing the very behavior of matter and energy at their most extreme, testing the laws of physics in a realm where they are pushed to the breaking point. In this way, the darkest objects in the cosmos become our brightest beacons for discovering the rules that govern everything. The cosmic particle accelerators powered by black holes demonstrate their ability to transform matter and energy, but this process raises a deeper question about the ultimate fate of the information that matter carries. This brings us to one of the most famous and enduring puzzles in all of science, the black hole information paradox. At its heart is a direct conflict between two pillars of modern physics. Quantum mechanics, the rules governing the very small, has a fundamental law: information is never truly destroyed. It can be scrambled beyond recognition, but in principle, the complete history of a particle, its properties and interactions, is always preserved in the universe. Now bring a black hole into the picture. According to Einstein's general relativity, when anything crosses the event horizon, it is lost to our universe forever, its information seemingly erased at the singularity. To make matters more perplexing, Stephen Hawking showed that black holes can slowly evaporate through radiation. If a black hole evaporates completely, what happened to all the information about every star, every bit of dust, every atom that ever fell in? Does it just vanish from reality, violating a core quantum rule? This is the paradox, a glaring contradiction that has fueled decades of intense debate and some of the most creative theoretical work of our time. Proposed solutions sound like science fiction, but they are serious physics. One leading idea is the holographic principle, which suggests that all the information about what fell into the black hole is not lost inside, but is instead encoded on its two-dimensional surface, the event horizon. It is as if the interior of the black hole is a three-dimensional projection of data stored on its boundary, like a cosmic hologram. Another possibility is that the information does escape, but not in any orderly way. It could be slowly and chaotically leaked out in the Hawking radiation itself, encrypted in a form of quantum static so complex it is virtually impossible to decode. There is even the speculative notion of a Planck scale remnant, a tiny, incredibly dense leftover from evaporation that holds all the information frozen for eternity. This intellectual struggle is far more than an academic exercise. It highlights a fundamental crack in the foundation of our understanding. General relativity and quantum mechanics, our two most successful theories, give completely different and incompatible answers when pushed to this extreme. The black hole information paradox is therefore a beacon, a glaring signpost pointing directly to the need for a deeper, unified theory of quantum gravity. Resolving this single puzzle would likely force us to rewrite our concepts of space, time, and reality itself. In this way, black holes are not just astronomical objects, they are the ultimate cosmic laboratories and catalysts, forcing the human mind to confront the very limits of knowledge and imagine a new physics waiting to be born. That profound conflict over information hints at a radical escape route, a theoretical shortcut woven into the very fabric of spacetime. The mathematics of Einstein's relativity contains a stunning possibility, a tunnel connecting two distant points in the universe or even bridging separate universes entirely. This is the wormhole, often called an Einstein-Rosen bridge. The equations suggest that the intense curvature of spacetime around a black hole could, in theory, connect to a mirror opposite, a hypothetical white hole where matter and energy only pour outward. Together, they could form a cosmic passageway. While this idea fuels countless science fiction stories, the reality for any traveler would be grim. The classic wormhole described by the equations is not a stable subway for spaceships. It is more of a mathematical curiosity, a fleeting ghost in the geometry of spacetime. The moment it forms, it would snap shut faster than light could travel through it, crushing anything inside. The deadly singularity at the heart of a black hole would act as an impassable barrier, a one-way shredder of matter. For a wormhole to become a traversable shortcut, something truly bizarre would be required: exotic matter with negative energy density. This is not antimatter, which still has positive energy. This is a hypothetical substance that would generate a kind of antigravity, propping the throat of the wormhole open against its own intense tendency to collapse. We have no evidence such matter exists or could be created in usable quantities. Yet the dream persists because the payoff is so magnificent. Physicists like Kip Thorne have rigorously explored what it would take. A stable, human-passable wormhole would be a gateway, allowing for travel between points that could be billions of light-years apart in an instant, effectively permitting faster-than-light journeys without breaking the universal speed limit locally. You would not be moving faster than light through space. Space itself would be providing the shortcut. It could connect different eras in time or serve as a bridge to other cosmic realms. This transforms the black hole from a symbol of finality into a potential cosmic connector, a hidden door in the architecture of reality. While it remains a speculative dream on the very edge of known physics, the wormhole idea endures because it speaks to a deep human longing to not just stare at the stars, but to one day walk among them. It suggests that the universe's most forbidding features might conceal its greatest gifts, turning the ultimate end into a possible beginning. The whispers of colliding black holes may hold a hidden resonance. After the main gravitational wave chirp fades, some physicists are straining to hear a faint, repeating echo. These subtle signals, if they exist, would be nothing short of revolutionary. They would challenge the classical No-Hair Theorem directly, suggesting the event horizon is not perfectly smooth. Instead, it might have a quantum structure, a kind of fuzzy or reflective wall just outside the point of no return. This quantum fuzz could be a manifestation of the theoretical Planck scale, the smallest possible length in the universe, where spacetime itself might have a granular, pixelated nature. When the violent merger sends gravitational ripples through this region, a tiny fraction of the energy might bounce back, creating a delayed and decaying echo in the data. Detecting this is a monumental technical challenge. The primary signal from a black hole collision is already an incredibly faint tremor in our detectors. Any echo would be exponentially weaker, buried deep within the random noise of the universe and the instruments themselves. Researchers use sophisticated statistical methods to comb through the data from observatories like LIGO and Virgo, searching for these ghostly patterns. It is like trying to hear the texture of a wall by listening to the faintest reverberation of a distant crash. The pursuit is a new frontier in observational physics, moving us from simply detecting black hole mergers to actively probing their fundamental architecture. A confirmed echo would be our first experimental glimpse of quantum gravity in action. It would provide tangible evidence that the rules of the extremely small do not just apply to particles, but also sculpt the most massive objects in existence. These potential whispers in the void are more than just data anomalies. They are clues to a deeper layer of reality, a hidden quantum surface on the edge of darkness. And if the boundary of a black hole can hold such complex structure, what does that imply for the chaotic, energetic maelstrom that feeds it? The theoretical whispers of quantum echoes hint at a spacetime structure so warped it could unravel causality itself. This brings us to one of the most mind-bending implications of all, the theoretical possibility that a black hole could function as a time machine. The key lies not in the black hole itself, but in the twisted region of spacetime surrounding it, the ergosphere of a rapidly spinning black hole. Within this zone, the frame dragging is so severe that it twists the fabric of the cosmos into knots. Some specific mathematical solutions to Einstein's equations, like the one for a rotating black hole surrounded by an infinitely long, rotating cylinder of exotic matter, allow for paths called closed time-like curves. These are not paths through space but loops in spacetime itself. An object following such a path could, in theory, travel along a trajectory that circles back to an event in its own past. It would be a literal loop in time, a cosmic roundabout where the exit ramp leads to yesterday. The concept is staggering, suggesting that under these extreme and artificial conditions, you could potentially witness historical events or even interact with a younger version of yourself. Yet this is where the dream crashes into physical reality. Most physicists argue that such paths are fundamentally unstable. The moment any real object, even a single atom, tried to traverse one, its own gravitational influence would create a feedback loop of infinite energy that would destroy the tunnel or require impossible amounts of exotic matter to stabilize it. It is a mathematical possibility that seems to be physically forbidden by the universe's own machinery. Stephen Hawking proposed a chronology protection conjecture, a poetic idea that the laws of physics inherently contain a safety mechanism, like a cosmic immune system, that prevents time travel to the past and thus protects the logical sequence of cause and effect. The famous grandfather paradox, where you travel back and prevent your own birth, illustrates the logical knots that would unravel reality. Nature, it seems, abhors a time loop as much as it abhors a vacuum. So while you will not be booking a ticket to the age of dinosaurs via a black hole anytime soon, the mere theoretical possibility is profoundly illuminating. It shows that black holes are not just objects in space, they are tools for thought, stretching our understanding of time from a rigid arrow into a malleable substance that can, in principle, be bent into a circle. They force us to confront the very foundations of causality, of what it means for one event to lead to another. In this way, they serve as the ultimate mathematical playground, revealing that the linear flow of time we experience may be a local condition, a calm eddy in a cosmos where the river of time can, in the most extreme corners, theoretically swirl back upon itself. This potential, however distant from practical application, adds a layer of profound wonder to their nature, transforming them from cosmic destroyers into lenses through which we examine the most fundamental architecture of existence. The theoretical possibility of time loops exists on a scale far smaller than the true giants that anchor the cosmos. Our own galaxy's central black hole, while impressive, is a modest neighbor compared to the true monarchs of darkness. The current record holder for sheer immensity resides in the heart of a galaxy called Home 15A. Its mass is not measured in millions of solar masses, but in tens of billions. This black hole is estimated to weigh a staggering 40 billion times more than our Sun. To grasp that scale, consider the size of its event horizon, the boundary of its gravitational dominance. If you could place this object at the center of our solar system, its event horizon would not just swallow the Sun. It would extend far beyond the orbit of Neptune, engulfing the paths of every planet and dwarf planet in a sphere of absolute darkness over 800 times wider than Earth's entire orbit around the Sun. It is not merely a point, it is a vast region of spacetime, a domain where its gravity is the only law that matters. These ultra-massive black holes are thought to be the ancient products of a violent cosmic history. They sit at the centers of giant elliptical galaxies, often found in the crowded cores of galaxy clusters. Over billions of years, they have grown through a relentless process of mergers, swallowing other black holes during galaxy collisions, and feasting on the vast reservoirs of gas funneled into the cluster's center. Their growth may have come at a great cost to their homes. The phenomenal energy released during their most active feeding phases likely blew away or heated up the galaxy's star-forming gas, effectively shutting down the birth of new stars. This left behind what astronomers call red and dead galaxies, vast swarms of old, red stars with no young blue ones, a silent testament to the black hole's past fury. Their scale is so vast it defies our everyday intuition about what an object can be. We call it a hole, but it is more accurate to think of it as a gravitational continent, a dark heart so massive it dictates the motion of thousands of galaxies swirling around it in a cluster. Studying these behemoths pushes our understanding of physics to the limit, probing the ultimate boundaries of how large a single concentrated mass can become. They represent the end result of cosmic evolution on the grandest scales, the final, quiet rulers of regions of space millions of light years across. Their silent, dark presence is a humbling reminder that the universe operates on a canvas of size and time we are only beginning to comprehend. The true scale of those supermassive giants forces us to look back to the very beginning, to a time before the first stars even existed. While most black holes are born from stellar death, a compelling hypothesis suggests a far more ancient origin story. In the unimaginable heat and density of the universe's first fraction of a second, tiny, violent fluctuations could have created black holes directly from the raw energy of the Big Bang itself. These hypothetical objects are known as primordial black holes, and they would be cosmic fossils, relics from the moment of creation. Unlike their stellar descendants, their masses would not be tied to the life cycle of a star. They could be almost any size, from a speck smaller than an atom to a behemoth heavier than 1,000 suns. This incredible range makes them a fascinating, if elusive, solution to one of cosmology's greatest puzzles, the nature of dark matter. The mysterious, invisible substance that makes up most of the mass in the cosmos could, in theory, be composed of a vast swarm of these ancient black holes drifting between the stars. If this were true, our solar system might be constantly traversed by these silent, dark ghosts. One could pass right through the Earth, its gravitational pull subtly tweaking the orbits of satellites or causing a fleeting, strange lensing effect as it bends the light from a distant star. We have never definitively caught one, but the hunt is on. Stephen Hawking's work on evaporation adds another layer to the mystery. He calculated that the very smallest primordial black holes, those with the mass of a small mountain, would have lost mass over the eons through Hawking radiation. Their final moments would not be silent. They would end in a spectacular, sudden burst of gamma rays, a final flash marking the evaporation of a universe-old relic. Astronomers scan the skies for these unexplained, pinpoint flashes of high-energy light, hoping to catch the death rattle of a Big Bang fossil. Other searchers look for the characteristic twinkle of a star as a primordial black hole passes in front of it, minutely magnifying its light through gravitational microlensing. Finding one would be a discovery of unparalleled importance. It would give us a direct, tangible sample of the universe in its infancy, a key to understanding the conditions of the Big Bang itself. It could finally illuminate the dark matter that shapes the cosmos. Primordial black holes represent a hidden chapter in the story of everything, a ghostly population of firstborn objects that may still wander the darkness, carrying the imprint of the very first moment. The death rattle of a primordial black hole would be a solitary flash, but the collisions of their stellar descendants create a far more complex and lasting resonance. A newborn black hole does not fall silent after the violent chirp of its birth. Instead, it rings, like a bell struck by a tremendous hammer. The fabric of its event horizon vibrates, sending out a final, decaying hum of gravitational waves. These are not random tones, but precise frequencies dictated by the black hole's fundamental nature. Physicists call this the ring-down, the quasi-normal mode oscillations of the black hole as it settles into its final, quiet state. The concept transforms the black hole from a static pit into a cosmic musical instrument. Just as the pitch of a bell depends on its size, shape, and the material from which it is cast, the ringing frequencies of a black hole depend solely on its mass and its spin. Nothing else matters. This elegant simplicity provides scientists with a powerful new test. By carefully listening to the ring-down signal in the data from observatories like LIGO and Virgo, researchers can perform a kind of cosmic fingerprint analysis. The specific tones they detect should match perfectly the predictions of Einstein's general relativity for a classic black hole. Any deviation, any discordant note in that gravitational song would be a revolutionary discovery. It could hint at something exotic lurking within the event horizon, perhaps a surface or a fuzzball of quantum strings, rather than the smooth, featureless boundary the equations predict. Theorists like Saul Tucholsky laid the mathematical groundwork for understanding these vibrations decades before we could hear them. Now, with each new merger detected, we are not just witnessing a catastrophic event, we are tuning into the aftertones, the settling music of spacetime itself. Analyzing this ring-down is like a master piano tuner listening to the decay of a single note to understand the integrity of the entire instrument. It allows us to probe the very nature of the event horizon, the last surface from which any signal can escape. In this way, the most destructive objects in the universe become composers, their brief, powerful songs written in the trembling fabric of reality, offering a direct test of gravity where it is most extreme. That ringing gravitational bell marks the aftermath of a merger, but a black hole's power is also written in the sudden, violent death of a star. When a star drifts into the gravitational domain of a supermassive black hole, its fate is not a quiet fade. The immense tidal forces, that difference in gravity between the star's near and far side, overcome the star's own gravity holding it together. In a cataclysmic process lasting only hours, the star is stretched and torn apart in what astronomers call a tidal disruption event. It is the ultimate cosmic shredding. Roughly half of the stellar debris is flung out into the darkness on long, hyperbolic trajectories, a ghostly remnant of the star's final moments. The other half rains down toward the black hole, swirling into a brilliant, temporary accretion disk. This sudden feast unleashes a tremendous flare of radiation, a beacon of light that can, for a few months, outshine every star in its host galaxy combined. For astronomers, this is a transformative opportunity. Most supermassive black holes, like our own Sagittarius A star, spend eons in a quiet, dormant state, offering few clues to their presence beyond the orbits of nearby stars. A tidal disruption event abruptly wakes such a sleeping giant, illuminating it with the light of its own destructive act. By analyzing the spectrum of this intense flare, scientists can perform a kind of cosmic autopsy. The light carries the chemical fingerprints of the destroyed star, revealing its composition. The rise and fall of the flare's brightness encodes the black hole's mass and the dynamics of its newfound, fleeting accretion disk. These events are cosmic rarity, estimated to occur perhaps once every 10,000 to 100,000 years in a galaxy like our own. Yet, with modern automated sky surveys like the Zwicky Transient Facility scanning the heavens nightly, we are catching them with increasing frequency, building a catalogue of these extreme occurrences. Each detection is a fleeting but brilliant laboratory, offering a front-row seat to the physics of gravity at its most destructive and luminous. It is a stark reminder that the serene spiral of a galaxy often masks a dynamic and violent heart, where a star's ending becomes a temporary lighthouse, illuminating the darkness for all to see. That brilliant flare from a shredded star is a fleeting beacon, but in April 2019, astronomers captured something far more permanent. The Event Horizon Telescope collaboration unveiled an image that instantly became an icon of science, the first ever direct visual evidence of a black hole's shadow. This was not a photograph of the black hole itself, for that is impossible. It was a portrait of its absence, a silhouette carved from light itself. The subject was the supermassive black hole at the heart of the galaxy Messier 87, a behemoth 6.5 billion times the mass of our Sun. The now famous fiery orange ring is not the event horizon. It is the light from the superheated gas in the accretion disk, bent into a perfect circle by the black hole's immense gravity. The dark central void, the shadow, is something even more profound. It is a region where light paths are captured forever by the event horizon, creating a darkness roughly 2.5 times larger than the actual point of no return. This shadow is the black hole's fingerprint on the fabric of reality. To capture this image from 55 million light-years away required an effort of staggering scale. The Event Horizon Telescope is not a single instrument, but a network of 8 radio observatories spanning the globe, from the mountains of Hawaii to the deserts of Chile and the icy plains of Antarctica. By synchronizing their observations with atomic clocks, they effectively created a virtual telescope as large as our entire planet, a technique called very long baseline interferometry. This gave them the resolution needed to see a donut on the surface of the moon. For days, they all stared at the same point in the sky, gathering petabytes of raw data that took years to painstakingly calibrate and assemble. The result was a breathtaking validation. The size and shape of that shadow matched the predictions of Einstein's theory of general relativity with remarkable precision. It proved that the object at the center of M87 is not just a dense cluster of stars or some other exotic object, but truly a supermassive black hole with the spacetime warping properties we had theorized for a century. This picture of nothing is in fact a detailed map of warped spacetime. It transformed the black hole from a mathematical abstraction and an indirect inference into a tangible, almost familiar cosmic phenomenon. It was a triumph of human collaboration and ingenuity, making the invisible visible and turning a theoretical monster into a known neighbor in our astonishing universe. That historic image of a black hole's shadow reveals a localized warping of spacetime, but the influence of these objects radiates far beyond their event horizons. The energy unleashed by a feeding supermassive black hole does not simply vanish into the void. It travels outward, becoming a dominant force that can sculpt the evolution of its entire host galaxy. This is the profound reality of quasar feedback, a cosmic balancing act of breathtaking scale. When a black hole is actively consuming matter, the resulting torrent of radiation and the focused beams of its relativistic jets flood the surrounding space with immense energy. This energy does something critical. It heats up the vast, cold reservoirs of molecular gas that drift between the stars. This gas is the cosmic nursery, the raw material from which new stars are born. When it is heated, the delicate process of gravitational collapse that forms stars is disrupted. In more extreme cases, the black hole's output can actually push this gas completely out of the galaxy, stripping it of its future building blocks. The effect is a form of galactic regulation. A brilliant, feeding black hole can, over millions of years, effectively quench star formation, turning a vibrant, blue spiral galaxy rich with young stars into a quiet, red elliptical galaxy populated by older, aging suns. Astronomers have observed a remarkable and telling correlation. The mass of a galaxy's central black hole is closely tied to the properties of the galaxy's central bulge of stars. This is not a coincidence. It suggests a deep, intertwined history of co-evolution. The black hole and its galaxy grew together, their fates linked through this cycle of feeding and feedback. The black hole's growth is fueled by infalling gas, but its own brilliant output then limits that very supply, putting a ceiling on both its own growth and the galaxy's star-forming potential. This transforms our understanding of their role. A supermassive black hole is not a passive ornament at the galactic center. It is an active participant in the galactic life cycle, a cosmic thermostat. Its occasional feasts release the energy that prevents the galaxy from overindulging, from forming too many stars too quickly and burning through its fuel. This feedback mechanism helps explain the diversity of galaxy shapes we see in the universe and why giant elliptical galaxies, often dominated by old stars, frequently harbor the most massive black holes. It reveals a stunning symbiosis between the smallest and largest scales in the cosmos, a singularity of infinite density. An object smaller than our solar system can govern the fate of a majestic structure 100,000 light-years across, its influence echoing for billions of years. That profound influence of black holes on their galactic homes is a one-way street of gravity and radiation. Yet the mathematics that describes them contains a startling possibility, a perfect mirror. If a black hole is a cosmic drain from which nothing escapes, its theoretical opposite would be a cosmic fountain, a white hole. This is a region of spacetime where nothing can ever enter, but matter and energy can only be expelled outward. The concept emerges naturally when you extend the solutions to Einstein's equations for a black hole and allow time to run in reverse. It is as if you took a film of something falling into a black hole and played it backwards, creating an object that eternally rejects anything that approaches its boundary. While no white hole has ever been observed, and many physicists doubt they could form in our universe, they are more than just a mathematical curiosity. They challenge our deepest assumptions about causality and the one-way arrow of time we all experience. One compelling idea suggests that a black hole might not end at a crushing singularity. Instead, its interior could connect, via a wormhole bridge, to a white hole in another region of spacetime or even another universe entirely. In this scenario, matter falling into the black hole here would be spewed out of the white hole there, offering a potential escape from infinite density. An even grander speculation proposes that the Big Bang itself, the explosive origin of our entire cosmos, could be viewed as a primordial white hole, a single event of ultimate emission. Another modern theory revisits the fate of an evaporating black hole. As it shrinks via Hawking radiation, approaching microscopic scales where quantum gravity dominates, it might not vanish completely. It could undergo a quantum bounce, transforming into a tiny, ephemeral white hole, releasing its final bit of stored energy and information in a final burst. This quartet of concepts, black holes, white holes, wormholes, and the Big Bang, forms a deeply interconnected theoretical family, each one shedding light on the others through the elegant lens of general relativity. Contemplating white holes forces a profound question. Does every cosmic phenomenon have its equal and opposite counterpart? They represent a perfect symmetry written into the laws of physics, a symmetry that our actual, messy universe may not manifest, but which illuminates the pristine logic underlying reality. They are a reminder that the story of the cosmos, as written by mathematics, may contain entire volumes, entire types of objects and events that our universe has simply chosen not to include in its current chapter. The search for them, or even the proof they cannot exist, pushes at the very edges of what is possible, challenging us to imagine a cosmos with different rules, where every end could be a beginning somewhere else. The theoretical possibility of white holes illuminates a perfect symmetry in the math, but in our actual universe, the most profound asymmetry might be hidden in plain sight. The largest-scale mystery in all of cosmology is dark matter, the invisible, unidentified substance whose gravity binds galaxies together. For decades, the leading hypothesis has pointed to an exotic, undiscovered particle, something beyond the standard model of physics. Yet a compelling alternative has never fully faded from view. What if a significant portion of dark matter isn't a sea of tiny particles, but a swarm of ancient, invisible objects? Specifically, primordial black holes within a certain mass range, perhaps weighing as much as a large asteroid. These would be the cosmic middle children of the primordial population, massive enough not to have evaporated away via Hawking radiation over the age of the universe, but small and dark enough to have completely escaped our telescopes so far. They would be pure gravity, drifting unseen through the galactic halo and between the stars. This idea elegantly connects two of the greatest puzzles in one stroke. It would simultaneously reveal the nature of the cosmos's missing mass and confirm the existence of those elusive fossils from the Big Bang. It proposes that the universe is not just sprinkled with black holes at galactic centers, but is fundamentally woven through with countless gravitational knots, each a silent relic of creation's first moments. The search for this specific class of primordial black hole is a masterclass in cosmic detective work. Astronomers don't look for light because there is none. Instead, they use a phenomenon predicted by Einstein himself, gravitational microlensing. The method is beautifully simple in concept, yet demanding in practice. If one of these dark, asteroid-mass black holes were to drift directly between Earth and a distant star, its gravity would act as a fleeting lens. For a period of days, weeks, or months, it would minutely bend and focus the star's light, causing a temporary, characteristic brightening. The entire galaxy becomes the detector, with surveys like the optical gravitational lensing experiment continuously monitoring hundreds of millions of stars, searching for these telltale, achromatic flashes in the data. It is a search for ghosts using starlight as the medium. No definitive, widespread population has been found yet, placing tighter and tighter constraints on how much of the dark matter could possibly be made of these objects. But the hunt continues because the payoff is so extraordinary. Finding them would mean that the dark matter shaping the grand architecture of the cosmos isn't an unknown particle, but a known, albeit extreme, manifestation of gravity itself. It would mean we live in a galaxy permeated by ancient, dark sentinels, each a frozen fragment of the universe's explosive beginning, their collective pull silently guiding the majestic rotation of stars. This final possibility transforms black holes from astronomical oddities or destructive monsters into potential foundational elements, the hidden scaffolding upon which the visible universe is built. The idea that black holes could be the hidden scaffolding of the cosmos is a modern revolution, but their journey into our imagination began not with certainty, but with a speculative leap in the age of reason. In 1783, an English natural philosopher named John Michell, contemplating Newton's laws of gravity and light, performed a remarkable thought experiment. He reasoned that if a star were sufficiently massive and compact, its gravitational pull would be so immense that not even light could escape from its surface. He called this hypothetical object a dark star. Independently, the French scholar Pierre-Simon Laplace arrived at a similar concept a few years later. These were not the black holes we understand today, but they planted a crucial seed, the first inkling that gravity could, in principle, create absolute darkness. That seed lay dormant for over a century, until Albert Einstein's theory of general relativity rewrote our understanding of gravity as the curvature of spacetime. Within months of Einstein publishing his equations in 1915, the German physicist Karl Schwarzschild found a solution describing the gravitational field around a spherical, non-rotating mass. His mathematics contained a boundary, a point of no return we now call the Schwarzschild radius. Yet this was seen by most, including Einstein himself, as a curious mathematical artifact, a theoretical extreme that could not possibly manifest in the real physical universe. For decades, black holes remained ghosts in the equations, dismissed as implausible singularities. The tide began to turn through a combination of tragic insight and relentless calculation. In the 1930s, a young Indian astrophysicist named Subramanian Chandrasekhar calculated that a white dwarf star above a certain mass limit would have no means to support itself against its own gravity. His work suggested a fate of infinite collapse, a conclusion so controversial it was publicly disputed by the eminent astronomer Arthur Eddington. Around the same time, Robert Oppenheimer, later known for his work on the atomic bomb, and his student Hartland Snyder used general relativity to describe the catastrophic collapse of a massive star, showing it could theoretically cut itself off from the rest of the universe. Still, the scientific community largely viewed these results as theoretical exercises. The modern concept finally crystallized with a new name. In 1967, the influential American physicist John Archibald Wheeler, during a conference talk, popularized the term black hole. It was a name that stuck, capturing the absolute, devouring nature of the phenomenon in two simple, evocative words. With a proper name came a surge of theoretical exploration. The work of Roger Penrose on singularities and Stephen Hawking's groundbreaking ideas about radiation and thermodynamics transformed black holes from mathematical oddities into thermodynamic objects with temperature and entropy, subjects worthy of serious physical law. Yet theory needed proof, and it arrived from the sky. The discovery of pulsars, rapidly spinning neutron stars, proved that stellar collapse could create incredibly dense remnants. Then, in 1971, astronomers turned their instruments toward a powerful source of X-rays in the constellation Cygnus, named Cygnus X1. The data revealed it was part of a binary system, a visible star orbiting an invisible companion with a mass several times that of our Sun, far too heavy to be a neutron star. The evidence was compelling. This dark companion could only be a black hole. It was the first strong observational candidate, a silent confirmation of decades of theoretical struggle. This long historical arc, from Mitchell's dark star to the confirmed detection of Cygnus X1, is a masterclass in the scientific method. It shows how human understanding evolves through a fragile dance of bold speculation, mathematical rigor, stubborn skepticism, and patient observation. Each fact we uncover today about black holes, from their spinning ergospheres to their gravitational waves, rests upon this foundation built by curious minds who dared to follow the equations into the dark. Their journey reminds us that the universe's greatest mysteries often begin as faint whispers in the mathematics, awaiting the technology and the courage to listen. And as we continue to listen, we are now uncovering clues that black holes might not be the end of the story, but could be connected to something even more fundamental, a theoretical framework that seeks to unite all the forces of nature into a single, elegant description of reality. The frozen clock and the gravitational chirp are more than scientific data. They are echoes from the edge of the possible. Our journey through these 25 facts reveals a truth far more astonishing than any single discovery. Black holes are not the end of understanding, they are the beginning. They are dynamic engines spinning at the limit of reality, cosmic regulators that sculpt galaxies, and profound puzzles that force us to rewrite the laws of physics. They challenge everything we think we know about space, time, and the very nature of information. Each fact we explored, from the silent shadow in Messier 87 to the theoretical whisper of a white hole, is a vital piece of a grand cosmic puzzle. This puzzle connects the fiery birth of the universe in the Big Bang to the majestic swirl of galaxies and the silent drift of dark matter. It is a story still being written, with every new observation from telescopes and gravitational wave detectors adding another sentence. The astronomer Carl Sagan once reflected that somewhere, something incredible is waiting to be known. Today, we know that black holes sit at the very heart of that search. They are the ultimate cosmic teachers, showing us where our current knowledge ends and the next great revelation begins. Let this knowledge be a spark. Let it ignite your own curiosity about the cosmos and our place within it. I would love to hear which fact reshaped your perspective the most, so share your thoughts and questions in the comments below. If you enjoyed this journey to the edge of physics, please like this video and subscribe for more explorations into the mysteries of space. Hit the notification bell so we can continue wondering together. Until next time, keep looking up. The greatest darkness, it turns out, holds the brightest light for understanding our incredible universe.